January 11, 1944, 26,000 feet above Oschersleben in central Germany. The outside air temperature reads -52 degrees Fahrenheit. Inside the number 2 engine nacelle of a B-17F Flying Fortress named Belle of the Brawl, a Wright R-1820 Cyclone is doing something that should be physically impossible. Its crankshaft is rotating at 2,300 revolutions per minute. At each of its 9 main bearing journals, the steel of the crankshaft is pressing against another piece of steel with a force exceeding 4 tons per square inch. The 2 pieces of metal are separated by a film of oil approximately 2/10,000ths of an inch thick. That is roughly the diameter of a human red blood cell. The aircraft is being shot at. 18-pound flak shells are exploding in close proximity, and the airframe is shuddering at frequencies that should set up destructive harmonics inside any rotating machinery. The engine has been running at high cruise power for 4 hours and 7 minutes. It has another 3 hours to go before it touches the ground again, assuming it touches the ground. The pilot does not think about the bearings. The engineer does not think about the bearings. The crew chief who signed off on the engine the night before in a Quonset hut at Thurley, England, did not think about the bearings, beyond the simple act of checking that the oil pressure read 45 pounds per square inch on the magneto check. Nobody who flew bombers in the 8th Air Force in 1944 thought about the bearings. They thought about flak. They thought about Focke-Wulfs. They thought about the cold and the fear and the fuel and whether the navigator had the wind right. They thought about 1,000 things, but never about the 4 small curved pieces of steel-backed silver alloy that were the only object standing between their aircraft and a runaway connecting rod explosively dismembering their engine in the thin air over Saxony. This is the story of why they didn't have to. Every modern aircraft engine of the Second World War operated on a paradox that, when you look at it directly, seems impossible. Inside the engine, steel parts rotated against other steel parts at speeds that would normally generate enough friction to weld them together within seconds. The pistons of a Pratt & Whitney R2800 double wasp moved up and down inside their cylinders 66 times per second at full power. Each piston was connected to the crankshaft by a connecting rod. The connecting rod transferred the explosive force of combustion, every combustion event peaking at roughly 1,200 pounds per square inch of cylinder pressure, into a rotational motion at the crankshaft journal. At the moment of peak combustion, the load on the crankshaft journal exceeded 6 tons per square inch. The journal was rotating at 2,700 revolutions per minute. The bearing surface between the connecting rod and the crankshaft journal had a sliding velocity at full power of approximately 35 feet per second. Steel cannot slide against steel at 35 feet per second under 6 tons per square inch of load. It will not work. It cannot work. The metals will gall, weld, tear, and fail within a fraction of a second.
The reason the engine ran instead of disintegrating was that the connecting rod was not, technically, touching the crankshaft. It was floating. Between the steel of the crankshaft journal and the steel of the connecting rod, there was a thin shell of softer metal, perhaps 15,000ths of an inch thick, bonded to a steel backing strip and pressed into the cap of the rod. Across the surface of that softer metal, oil under pressure from the engine's lubrication system formed a hydrodynamic film. The crankshaft journal rode on this film of oil. It never actually touched the bearing surface, except at the moment of starting, the moment of shutdown, and during brief excursions under extreme load when the oil film thinned. The bearing's job was to survive those excursions without destroying itself, to absorb any small contaminant that found its way into the oil, to dissipate the heat generated by friction, and to maintain its dimensional accuracy to within a few 10,000ths of an inch for hundreds, then thousands of hours, across thermal cycles ranging from -50 in the upper atmosphere to over 400 degrees Fahrenheit inside the engine after a hard climb. It was the most demanding metallurgical assignment in the entire aircraft, and it was assigned to a piece of metal smaller than a man's palm. The Norden bomb sight is famous. The Browning machine gun is famous. The Merlin engine is famous. The B-17 itself is famous, photographed and filmed and memorialized in concrete at airfields across the American Midwest. The men are famous, properly so, and their stories are told and retold every year on the anniversary of every raid. But the bearings are not famous. There is no monument to them. There is no museum exhibit. They appear in no documentary. The companies that made them, Cleveland Graphite Bronze, Federal Mogul, and Johnson Bronze, are footnotes in industrial histories that themselves are rarely read. And yet, without those small curved shells of bonded metal, not one of the famous things could have happened. Every Merlin in every Spitfire, every R-2800 in every Thunderbolt, every Allison in every P-38, every Cyclone in every B-17, every Twin Wasp in every Liberator, every R-3350 in every B-29. None of them would have run for more than a few hours. The 8th Air Force would have stayed on the ground. Berlin would not have been bombed. The story of how that did not happen, of how a small company on the east side of Cleveland, Ohio, managed to produce a bearing capable of surviving conditions that bearings had never been asked to survive before, and then to produce them in quantities no one in 1939 would have believed possible, is the story of one of the most consequential pieces of metallurgy in the 20th century. It begins, like so many of these stories, with a name almost no one remembers. Ben Hopkins was the son of a Cleveland businessman with no particular distinction. In 1919, Hopkins took an idea, an interest, and 20 employees and rented space at 2906 Chester Avenue in Cleveland to start a company he called Cleveland Graphite Bronze. The name described, at the time, a fairly mundane product. CGB made what were called self-lubricating bushings for the automotive industry. These were small cylindrical sleeves of cast bronze into the inside surface of which graphite had been baked or pressed under heat. The graphite served as a solid lubricant, which meant the bushing could rotate around a steel shaft for thousands of hours with minimal oil. They were used in places where adding an oil supply was inconvenient, in suspension parts, in steering linkages, in accessory drives. They were unglamorous, but they were essential, and Hopkins built a business making them. What changed everything about Cleveland Graphite Bronze, and eventually about every aircraft engine flown by the Allied Air Forces in the Second World War, was something CGB engineers developed in 1930. It was called the thin-wall bearing. Until 1930, the standard way to make an engine bearing was to pour molten Babbitt metal, a soft alloy of tin, antimony, and copper, invented by a man named Isaac Babbitt in Massachusetts in 1839, directly into a cast iron or bronze housing inside the engine. The Babbitt would solidify, and a machinist would then bore and scrape it by hand to fit the crankshaft journal. The process was slow. It required skilled labor. The bearings were thick, sometimes 3/8 of an inch of Babbitt over a bronze backing, which meant they had significant thermal mass, slow heat dissipation, and limited fatigue strength. If the bearing failed, the entire engine had to be partially disassembled, the old Babbitt melted out, new Babbitt poured in, and the whole thing rebored. For automobile manufacturers building tens of thousands of engines on assembly lines, this was an enormous bottleneck. For aircraft engines spinning faster and faster every year, it was rapidly becoming impossible. The bearings were the limiting factor. The thin-wall bearing did away with all of that. The engineers at Cleveland Graphite Bronze took a strip of low-carbon steel, perhaps 50 thousandths of an inch thick. To one face of that steel strip, they metallurgically bonded a layer of copper-lead alloy, approximately 15 thousandths thick. The copper provided strength. The lead, dispersed in tiny droplets through the copper matrix, provided the soft running surface against which the crankshaft journal would slide. They then rolled the bimetallic strip around a forming die, producing two semicircular shells that snapped together inside the connecting rod cap or the main bearing saddle. The shells were precision finished at the factory to within 10 thousandths of an inch of nominal. They required no scraping, no hand fitting, no boring. An assembly line worker could pull a pair of shells from a box, lay them into the bearing housing, torque the cap to specification, and have a finished precision bearing in less than a minute. If a bearing failed in service, a mechanic could remove the cap, lift out the worn shells, drop in new ones, and have the engine running again in an hour. The thin section meant the bearing dissipated heat almost 10 times faster than the old cast Babbitt designs. The steel backing gave it fatigue strength the old bearings could only dream of, and the cost in skilled labor per engine dropped by an order of magnitude. In 1930, the year the thinwall went into production, Cleveland Graphite Bronze had a few hundred employees. By 1937, the company was making 183 million bearings per year. Its workforce had grown to 2,300 people. The thinwall had become the standard bearing in every Detroit automobile, in Caterpillar tractors, in Cummins diesel trucks, in Alice Chalmers combines. American industry, the most rapidly mechanizing economy on Earth, ran on Cleveland Graphite Bronze's bearings, and most of the people whose lives depended on those bearings every day they drove to work had never heard of the company.
Around this time, an Englishman walked into the lobby of CGB's headquarters on East 72nd Street in Cleveland and sat down on a sofa. His name was Guy Anthony Vandervelde, and he was the son of Charles Vandervelde, founder of an English electrical components company called CAV. Tony, as he was called, had been a motorcycle racer at the Isle of Man, a car racer at Brooklands, and was now running a small bearing subcontractor called ONS Oilless Bearing Company that supplied parts to his father's electrical business. He had heard, somewhere, perhaps from an American engineer named Delmar Roos who worked at Studebaker, that there was an American company in Cleveland making a revolutionary new bearing. Vandervelde had crossed the Atlantic by steamer specifically to acquire the European manufacturing license. The story, told by his biographers, is that he sat on that sofa in the CGB lobby for 6 days. He did not have an appointment. He did not have an introduction. He simply sat and waited and made it clear he was not leaving until someone with authority spoke to him. Eventually, someone did. He left Cleveland with a licensing agreement that allowed him to manufacture thinwall bearings in the United Kingdom, and he went home and founded a company called Vandervelde Products in Acton, West London. That license, secured by a stubborn racing driver son of an electrical industrialist who refused to take no for an answer, would within a decade put Cleveland Graphite Bronze's bearings inside every Rolls-Royce Merlin engine ever built. The bearing shells in the connecting rods of the Spitfires that flew the Battle of Britain were Vandervelde thinwalls, manufactured in Acton under license from a company in Ohio. W.A. Robotham, the chief engineer at Rolls-Royce, later wrote in his memoirs that no British company had been able to develop bearings of equivalent quality before the war, and that without the American license and the manufacturing capability Vandervelde built around it, the Merlin engine would have been crippled by bearing failures from the start. Robotham knew. He had been there. He had watched the failures, the recalls, the engines stripped on the bench, the connecting rods sent back to the foundry. The thinwall, made in Cleveland, copied in Acton, was the difference. But the thinwall as it existed in 1937 was an automotive bearing. It was excellent for what it did. It was not, by itself, an aircraft bearing. Aircraft engines operated in a different regime entirely. The R-1820 Cyclone in a B-17 produced 1,200 horsepower from a displacement of 1,820 cubic inches. That is 66 horsepower per liter, a specific output that exceeded any production automotive engine of the era by more than a factor of 2. The R-2800 Double Wasp produced 2,000 horsepower, climbing to 2,800 with water injection by 1944 from 46 liters. The R-3350 in the B-29 produced over 3,300 horsepower, peaking at 3,700 in the experimental Wright Cyclone 22 derivative. These were extraordinary numbers. They were achieved by running the engines at compression ratios as high as 7:1 on 130-octane aviation gasoline at manifold pressures above 45 inches of mercury, with cylinder pressures peaking around 1,200 psi. The connecting rod loads in a double wasp at full power were almost 3 times higher than the loads in any contemporary truck engine, and the rod was being swung through that load 33 times per second, every second, for hours on end while the engine was being bounced and pitched and yawed and shot at. The copper-lead thinwall, designed for automobiles, could not handle it. Engineers at Cleveland Graphite Bronze had known this would be a problem since the late 1930s, when conversations with Pratt & Whitney and Wright Aeronautical revealed how aggressive the next generation of aircraft engines were going to be. CGB had a research division by then, and it began a development program, quietly, 2 years before Pearl Harbor, to design a bearing material that could survive the new engines. The solution they arrived at was, on paper, ridiculous. They proposed plating the working surface of the bearing not with lead, not with tin, not with babbitt, but with silver. Pure silver electroplated onto a steel backing strip in a layer perhaps 12/1000ths of an inch thick. Over the silver, they would then plate a thin overlay of lead tin or lead indium, just 1 or 2 thousandths thick, to give the bearing the soft running-in surface it needed. The silver provided the load capacity and the heat conduction. The overlay provided the embeddability, the ability to absorb a small particle of carbon or wear debris without scoring the crankshaft. Together, the composite could handle pressures that pure copper lead could not even approach. Silver was, of course, expensive. It was also strategically controlled. The United States Mint held enormous reserves of it. The fact that the bearing required only 12/1000ths of an inch on a strip of steel meant that, by weight, the silver consumption per bearing was actually quite small. By the standards of conventional silver applications, photographic film, electrical contacts, tableware, the bearing program was a modest user. The Manhattan Project would eventually borrow 14,000 tons of silver from the West Point Bullion Depository to wind the electromagnetic coils of its uranium enrichment calutrons, an episode that has rightly become famous. The silver-bearing program, far smaller and started years earlier, has not. But by the standards of the metallurgical knowledge of 1939, plating silver onto steel and bonding it well enough to survive the connecting rod cap of a high-output radial engine was a problem of breathtaking difficulty. Silver does not naturally adhere to steel. The thermal expansion coefficients are different. Cyclical loading at high temperatures tends to make silver-on-steel interfaces delaminate. CGB engineers spent 2 years working through the chemistry. They developed a multi-step plating process that began with a strike layer of copper, perhaps 100 millionths of an inch thick, followed by the silver, followed by another flash of copper as a diffusion barrier, followed by the lead-indium overlay. The whole stack-up had to be deposited evenly, without porosity, without inclusions, and bonded so well that nothing short of catastrophic engine failure could separate the layers. By the spring of 1941, when the United States was not yet at war but was clearly building toward it, Cleveland Graphite Bronze had a silver overlay aircraft bearing in production. Pratt & Whitney specified it for the master rod of the R2800. The master rod in a radial engine is the single connecting rod that bolts directly to the crankshaft, with all the other rods in that bank of cylinders attached to it through articulated knuckle pins. The master rod bearing is the single most heavily loaded component in the entire engine. It is the choke point. If it fails, the engine instantly stops, then disassembles itself violently. Pratt & Whitney's decision to base the R2800 master rod bearing on the CGB silver overlay design was an act of faith in a company that had never before built an aircraft component for a wartime production program. By 1944, that bearing was inside every P-47 Thunderbolt, every F-4U Corsair, every F-6H Hellcat, every B-26 Marauder, every A-26 Invader, every C-46 Commando, and every other airframe powered by the Double Wasp. Pratt & Whitney built over 125,000 R2800 engines during the war. Every one of them had a silver overlay master rod bearing, and the overwhelming majority of those bearings, or their licensed equivalents made by Federal Mogul and Johnson Bronze under wartime cross-licensing agreements, traced back through metallurgical pedigree to the development work done by a handful of engineers in a brick building on East 72nd Street in Cleveland. The scale-up was the second miracle. In 1939, Cleveland Graphite Bronze employed about 2,300 people. By 1945, it employed over 7,000.
3 production shifts ran around the clock, 7 days a week, in a plant complex that had expanded onto a new site at 17,000 St. Clair Avenue, with a building so large that the company sometimes had trouble finding workers fast enough to fill it. The bearings poured out by the millions. By the middle of 1944, CGB alone was producing somewhere over 200 million bearings per year, of which a steadily growing fraction were aircraft grade. The Federal Mogul Corporation in Detroit, which had its own bearing technology based on a copper-lead alloy called C50 developed in their research labs in 1934, expanded similarly. So did Johnson Bronze in Newcastle, Pennsylvania. Together, the 3 companies became the structural foundation of every Allied aircraft engine program. The work was difficult, and the workers were not necessarily prepared for it. The vast majority of pre-war bearing manufacturing employees had been men, often skilled tradesmen with years of experience. By 1942, those men were largely in uniform. CGB and Federal Mogul, like every other defense contractor, replaced them with women. Whole new training programs had to be invented. Standards had to be enforced through inspection rather than craft tradition. The plating tanks, where the silver and copper and indium were electrochemically deposited onto steel strip, became some of the most carefully monitored chemical operations in American industry, because variations of a few % in plating bath composition could produce bearings that failed in service in ways that killed pilots. The quality control departments grew larger than the original manufacturing departments had been. Every batch of bearings was sampled, sectioned, etched, examined under microscopes, weighed for plating thickness, pulled to destruction on tensile testers. Bearings that failed any test were scrapped, the metal returned to the refining stream, the lot rejected.
The tensions inside the plants were considerable. Cleveland Graphite Bronze, on September 6 of 1944, became the site of one of the most consequential labor actions of the wartime home front. An employee named Elmer Torok had broken a 75-cent padlock to get into his locker. The company fired him. The union, the Mechanics' Educational Society of America, walked out. 5,000 workers stopped making bearings. The strike lasted until November 11th, when the United States Army formally seized the plants under the authority of executive order. For 2 months, in the autumn of 1944, the 8th Air Force was bombing Germany using bearings that had been made in a factory under direct military control because the labor force and management could not agree on how to handle a broken padlock. The strike and the seizure did not produce a serious shortage of aircraft bearings because Federal Mogul and Johnson Bronze had built up enough capacity by then to cover the temporary gap. But the episode reveals how thin the margin actually was. The whole production system, glittering and unprecedented in its scale, depended on the continued cooperation of thousands of women and men who were exhausted, underpaid by the standards of the cost of living, and increasingly aware that their lives had been put on hold for the duration of a war that, by 1944, seemed to be ending without them. What the bearing did in the engine deserves to be understood in detail, because the magic was not in any one thing, it was in the integration of many things. When a B-17 took off from a base in England on a winter morning in 1944 with 4 R-1820 Cyclones at maximum continuous power and a full bomb load straining the wing spars, the bearings in those 4 engines began their working day having sat all night at temperatures around 0 degrees Fahrenheit. The oil in the sumps was viscous and slow. For the first 30 seconds of operation, before the oil pressure built and the bearings developed full hydrodynamic film, the silver overlay was the only thing standing between the crankshaft and catastrophic galling. The soft lead-indium top layer absorbed the rubbing. As the engine warmed, the oil thinned, the pressure climbed, and the hydrodynamic film established itself. By the time the bomber lifted off, the bearings were running on oil, not on metal-to-metal contact, and the silver underneath was carrying the load it had been designed to carry. As the aircraft climbed to 26,000 feet, the engines drew thinner and thinner air. To maintain power, the turbo superchargers spun up to forecast revolutions exceeding 20,000 RPM. The cylinders inhaled denser charges of fuel and air.
combustion pressures rose. The connecting rod bearings felt every one of those pressure spikes. The silver, with its remarkable thermal conductivity, second only to copper among the common metals, carried the heat of friction away from the running surface and into the steel backing, and from there into the oil stream. The oil, returning to the cooler in the nacelle, dumped that heat into the slipstream at 60 degrees below zero. The bearing never overheated. When the formation reached its target and the bomb bay doors opened, the bombardier flew the airplane through the bomb site for the final 2 minutes of the run, and the engines had to hold a precise power setting against the increased drag. The bearings, by then 5 hours into the mission, were still maintaining the few 10,000ths of an inch of running clearance they had been built with. They had not worn measurably. They had not lost their dimensional accuracy. They had not delaminated. They were simply, quietly, doing their work, while the men in the airplane focused on the things that needed focus. After bomb release, the aircraft turned for home, descended, throttled back, and eventually landed. The crew climbed out and went to the mess. The engines were cooled, inspected, and made ready for the next mission. The bearings were not changed. They would not be changed until the engine reached its overhaul interval, which by late 1944 had been extended to 800 hours of operation. They would be checked at every 50-hour service, sampled by oil analysis, and replaced only if there was specific reason to do so. Most bearings completed their full overhaul cycle without removal. The 8th Air Force ran its engines essentially the way a trucking company ran its trucks, on the assumption that the bearings would last, and they did. The Germans, by contrast, had a problem they could not solve. German aircraft engines, particularly the Daimler-Benz DB605 in the Messerschmitt Bf 109 and the BMW 801 in the Focke-Wulf 190, were excellent designs in many respects. The BMW 801 was a 14-cylinder radial of 76 liters displacement, capable of 1,700 horsepower, fitted with a fully automatic engine management system years ahead of its Allied contemporaries. The DB605 was a beautifully made inverted V12 with direct fuel injection that allowed the aircraft to perform negative G maneuvers that early Merlins could not match. These were technically sophisticated engines, but their bearings were not made of silver. German bearing manufacturers, primarily firms in southwest Germany and Austria, continued through the war to rely on lead-bronze and copper-lead designs descended from interwar automotive practice. They were good bearings by the standards of 1938. They were not good bearings by the standards of 1944. As German engines were progressively uprated to extract more power from the same displacement in response to Allied numerical superiority in the air, the bearings began to limit them. Time between overhauls on Luftwaffe engines, which had been 300 hours in 1940, fell to 100 hours by 1944. Some operational reports mention squadron averages of 50 hours between overhauls. German pilots flew their aircraft knowing that the engines were essentially disposable, that they would be replaced or rebuilt many times during the operational life of the airframe, that running the engine at maximum power for more than a minute or two risked seizing it. The British, with their American licensing arrangement through Vanderbilt, did not have that problem. The Merlin engine, fitted with steel-backed lead-bronze bearings derived from the American thinwall and later improved with silver overlay technology, achieved overhaul intervals of 250 hours and more by 1944. The Americans had it even better. Our 2800 engines in operational service routinely exceeded 600 hours between overhauls. A P-47 pilot could fly the same airplane, the same engine, for the duration of an entire combat tour without ever having the engine torn down. This was not luck. It was the cumulative effect of thousands of small metallurgical decisions, of which the bearing was perhaps the most important single one. It is what made the air war winnable. It also made it possible to project American air power on a scale that, until 1942, no military force on Earth had ever attempted. By the spring of 1944, the United States was flying combat missions simultaneously over Germany, France, Italy, the Balkans, the Marianas, the Philippines, Burma, and China. The 8th Air Force in England had 1,800 heavy bombers on operational status. The 15th Air Force in Italy had over 1,000. The 20th Air Force, just forming up for the strategic bombing of Japan, had several hundred B-29s coming online. The naval and marine air components had thousands more carrier-based and land-based aircraft scattered across the Pacific. Every one of these aircraft had engines. Every engine had bearings. The bearings did not fail. The engines ran. The aircraft flew. The bombs were dropped. The war was prosecuted to its conclusion by an Air Force that did not, except in the very rarest of cases, have to scrub a mission because of an engine reliability problem. There were exceptions. The Wright R-3350 duplex Cyclone in the early B-29 had a notorious history of engine fires during the first year of operations, and those fires were not caused by bearing failure, but by problems with the crankcase and the cylinder heads in conditions of overheating during prolonged climbs from tropical airfields. The R-3350 bearings, made by the same firms using the same metallurgy as the other engines, performed essentially as designed. Once Wright Aeronautical solved the cooling and induction problems, the engine became one of the most reliable in the inventory and continued in service into the 1950s in the Lockheed Super Constellation and the Douglas DC-7 with the same fundamental bearing architecture it had carried over Tokyo.
Charles Kettering, the General Motors research executive whose obsession with diesel engines produced the GM 6046 that ended up in Sherman tanks, knew Ben Hopkins. The two of them had been part of the same network of Cleveland-area industrial engineers who had spent the 1920s and 1930s building, almost without intending to, the foundations of what would eventually become the American war machine. Hopkins did not live long enough to see all of what his work made possible. He died in 1958, less famous than Kettering, less wealthy than Vandervelde, having spent his life in the unglamorous business of selling bearings. His company, Cleveland Graphite Bronze, was renamed Clevite in 1952 when it began moving into electronics and was eventually absorbed by Gould Inc. in 1969. The brand name Clevite still exists, attached to a division of Mahle GmbH of Germany, and it still makes engine bearings, and those bearings are still used in performance and racing applications around the world. The silver overlay technology that came out of the wartime research has continued to evolve, and modern aerospace bearings for turbine engines and high-performance reciprocating engines still trace their genealogy back to the work done in Cleveland between 1939 and 1942. The basic geometric concept of the thin-wall bearing, a precision-formed bimetallic shell that snaps into a connecting rod cap, is the universal standard in every internal combustion engine manufactured anywhere in the world today, from a one-cylinder Honda generator to a 14-cylinder marine diesel. Tony Vandervelde, the Englishman who had refused to leave the lobby in Cleveland in 1931, used the fortune he made from licensed bearing production during the war to go racing. In 1958, his small team won the inaugural Formula One Constructors' Championship with a British-built car powered by a four-cylinder engine that was, in essence, a rebadged Rolls-Royce military engine fitted with Vandervelde thin-wall bearings. The team was called Van Wall, a name Vandervelde had built by fusing his own name with the trademark of the product that had made him rich. He died in 1967, his racing team disbanded, his bearing company on the verge of being absorbed by a larger British conglomerate. He left behind a few photographs of himself in racing overalls, a few trophies, and the silent legacy of having brought to Britain the technology that had kept the Merlins running over the Channel in 1940. W.A. Robotham, the Rolls-Royce chief engineer, wrote in his 1970 memoir, Silver Ghosts and Silver Dawn, that the licensing of the Cleveland Graphite Bronze thin-wall bearing was, in his assessment, the single most important piece of metallurgical assistance the British engine industry received from the United States during the entire interwar and wartime period. He noted that Vandervelde, whom he had personally found extraordinarily difficult to deal with throughout his career, had performed a service the importance of which historians would probably never fully recognize. He was correct on that last point. Historians have not recognized it. The bearing,
The small, curved shell of steel backed with copper and silver and indium and lead sitting in the cap of a connecting rod inside an engine, inside a nacelle, inside a wing on an airplane flying over Germany never asked for recognition. It did its work, which was to hold a steel shaft 6/1000ths of an inch away from another steel shaft, while one of them rotated at 2,700 revolutions per minute under tons of cyclical load for hundreds of hours in temperatures from -50 to 450 Fahrenheit without failing. That was the assignment. It performed the assignment. The men who designed the bearing knew what they had built. The men who flew behind it did not. The historians who wrote about the war later did not. And so the story of the bearing has remained quiet, while louder stories about Spitfires and Mustangs and flying fortresses have filled the books and the films and the public imagination. But every Merlin had 8 of them on the crankshaft and 12 more on the connecting rods. Every R-2800 had 22 of them per master rod assembly. Every R-3350 had more than 30. Multiply by the number of engines built, multiply again by the number of missions flown. The bearings of the Allied air forces in the Second World War numbered in the hundreds of millions. They were made by women and men working 3 shifts in factories in Cleveland and Detroit and Newcastle and Acton, who did not know what aircraft their bearings would end up in, who did not know what cities those aircraft would bomb, who did not know what young men would fly those aircraft home or not home. They knew only that the bearing in front of them needed to be within 10/1000ths of an inch of nominal, with 12/1000ths of silver bonded smoothly to the backing strip, with no porosity in the plating, no inclusions, no delamination at the corners. They built the bearings to specification. The bearings did their work. The engines ran. The war ended. And somewhere over Oschersleben in January of 1944, 4 R-1820 Cyclones in a B-17 named Belle of the Brawl carried 10 young men through a sky filled with flak and fighters and brought them home on bearings made by a company in Cleveland that no one in the airplane had ever heard of. That was enough. In a war decided by what worked, it was more than enough.